For my Choose Your Own Adventure lab, I chose to analyze the motion of the slinky. The motion of the slinky was analyzed and modeled in order to predict its motion considering effects from gravitational force. Tracker was used to analyze the video and GlowScript was used to model the object's motion. The momentum principle, gravitational force constant, and drag force equation were used to construct the model. The experimental data shows the object falling at a higher speed than predicted by the model, and the object appears to have fallen further than the model predicted. We have a few initial conditions, including our mass of our slinky to be 0.204 kilograms, our initial position, mainly focusing on the y-axis, to be somewhere close to 0, and then negative 0.426 meters. I chose the origin to be the bottom of the slinky, and the measurements were calibrated with the height of this man. Newton's first law in velocity update and position update form was used to predict the object's motion. The two forces acting on the object are tension and gravitational force. And then as the bottom of the slinky falls, only drag force and gravitational force are acting on the system. The system is the slinky, while the surroundings is the Earth. So here we go right into our code. We have inserted our mass, our initial position, and our initial velocity. We also have the gravitational constant and the drag force constant. Unfortunately, this, the closest I could get the data or the measurements was when this value was 0. So this will be discussed further in physics errors. The first iteration is during the time period between when the slinky was first released and when it is fully compressed. Over here we have our tension force, our weight force, and our net force equations, as well as our velocity update and position update equations. In our second iteration, we have the time from when the bottom of the slinky first begins to move to when it hits the ground. Again, we have our net force equations, including the drag force, as well as the weight force, and our velocity update and position update equations in code. To the right, we have our results. We see our experimental data in blue and our model data in orange. These values are very similar initially. However, once the bottom of the slinky begins to move, the experimental data has a greater velocity and does fall a greater distance. Sources of error include estimation of frames per second in Tracker, as well as estimation of the mass of the object and the calibration height, as well as inconsistent center of mass and incorrect estimation of time spent in static equilibrium. For our additional questions, we have, why did the bottom of the slinky remain stationary for a brief period of time before falling? Initially, the slinky is experiencing static equilibrium. The force of tension is equal in magnitude and opposite in direction to gravity. Since these are the only two forces acting on the system, the bottom of the slinky does not fall. Thank you for watching.